Welcome to EDU World Space.
So assume that we have the following situation. We have a positive curve like this. Here this is the x-axis and that is the y. This is the curve of y is equal to f of x. And we have some points here, 2 points here, A and B. And assume that we compute the area of the surface of revolution. The surface of revolution rotating about the x-axis. That function that will give us something like this. If we rotate that, we're going to obtain something like that. And so in that region, this region has some surface S of f that is equal to 2 pi times the integral from a up to b of f of x. That is the way to compute the area of surface, the rotation, surface of rotation about x. This times 1 plus the derivative of our function squared dx. So assume that you have that this for those two numbers is s of f, and that this curve has length L. So the length of a curve is the length of that curve is this number, the integral of this component here, f prime squared dx. This is the ds. So the length of this curve would be just the integral from a up to b of ds, the differential of length of the curve, that is ds. So now in this situation, what if we have our same function, but we consider some number c, some number here c, some positive number, and we're gonna make the new function g of x is equal to our function f of x plus that constant plus c. So it would look like, well, like we have our function here, and this is f, and the translated function would be like moving up. This is g, moving up this function by c units. So the obtained surface by rotating g, well, it would be also from a up to b, it would be like this wider shape that has sort of like the same form as the surface S of f, but with a wider radius. So it would be like this shape here from the same points A and B. So S sub f, S sub g, which is the surface of revolution, about the x-axis. So this would be the integral from a up to b of 2 pi times g times the integral times the square root of 1 plus g prime squared dx. But well, if we translate it from this equation, if we translated g f by a constant, well, then we have that f prime is equal to g prime. So that this part over here this is precisely all the same, but considering that with f, so that we have 1 plus f prime squared, that is this component here, and then well f, g is f of x plus c, so that this s of g is going to be equal to this integral 2 pi times the integral from a up to b of this, and then well can multiply this by that and then by that and separate the two integrals, so that the surface area of about rotating g about the x-axis, from rotating g about the x-axis would be 2 pi the integral from a to b of f of x times the square root of 1 plus f prime squared dx, and then plus c, and well c is a constant, so we can pull that out of the constant integral c times 2 pi the integral from a up to b of this is square root 1 plus f prime squared dx. So well, these are quantities that we know. So this part is s sub f, so the area of the surface of revolution by rotating the original function s sub f is precisely that number, and well, this is that number plus you have these constants 2 pi times c. Well, for c positive number, so it has to be positive, and then this term over here is the length of the curve L, which is we have that over here is the integral from a up to b of the square root of 1 plus f prime squared dx is that, so this is L, so that will be L. So the surface of the area of the surface of revolution of rotating g is the area of the original function plus 2 pi times c times L, and that is the area of this modified surface.